welcome everybody. We're gonna take about an hour here and go over some ignition fundamentals. Anybody that's new to the business, I'm sure will pick up a lot of information here. Any of the old timers, bear with me that a lot of this will be redundant for you, and you'll have to live through it. But we'll just go ahead and move on. I put in one slide for the inductive ignition system. For anybody that's new, the inductive ignition system was pretty popular back in the 60s and 70s, maybe into the early 80s, but they basically have gone by the wayside. I don't really know of anybody really running them anymore, and I also don't know of anybody that's actually building them anymore. The Nelcos and the companies that actually built them, I think, have pretty much gone out of business or quit building inductive ignition systems altogether. Basically, the coils in an inductive system worked as both the storage and the energy transfer medium. So it wasn't the greatest way to send energy out to the spark plug. Ultronic never built an inductive ignition system, and that was one of the reasons, because of the way they stored energy in the coil. The coils also served as the current limiting device. And an inductor is pretty inefficient energy storage medium. So basically the energy in versus the energy out is pretty poor. So like I said earlier, this next bullet point, Ultronic decided never to build an inductive system. An inductive system has very long duration. So there's a pro and a con to that. One of the cons of having very long duration, and I'm talking in the 600 to 1,000 microsecond range, a very long spark, is that that long spark would wear out spark plug prematurely. That was one of the cons. And one of the pros was that if you had a poor mixing big bore engine, then sometimes it benefited from that long duration spark. So that was one of the pros to an inductive system. Some of the characteristics of a CD ignition: we use basically a capacitor to store the energy. So that the capacitor delivers low current draw and a reduced heat dissipation. And you can get secondary voltage up to 50,000 volts. It's possible and may be needed for lean burn engines or high BMEP, high horsepower applications. You may need that 50,000 volts. Some of the other characteristics of CD ignitions: because of the shorter secondary voltage rise times, you have a reduced voltage bleed off during that rise. That improved the ability to fire fouled spark plugs over the old inductive system. And I put this the bottom bullet point in just yesterday. Basically, the formula for energy out of an ignition system is E is equal to half a CV squared. There's a reason I put this in here, because just because one ignition system has 200 volts primary and another has 330 volts primary doesn't mean the latter has more energy to the actual spark plug. And that came up a lot when we had a lot of competition in the ignition business with 3 or 4 different companies making ignitions. But this is also true of our own systems. We have systems that put out 200 volts, and we have systems that put out 330 volts. And unless you know the actual primary voltage, which is the half the CV squared is the V there, and you also know the capacitor size, you can't figure out what energy is coming out of a competitor's ignition system or even our own. So just because somebody says yours got 200, mine's got 330, doesn't make the 330 volt system a better system with more energy. And the example I put down below is just take a standard CPU 95 in the E3, E1, E2, E3 being the highest energy level. You're going to see 180 volts primary out to the bottom side of the coil, or the primary side of the coil. So if you take that formula, 180 volts squared, which would be times another 180 volts, you're at 32,400. You multiply that by half of the size of the capacitor. That particular system has an 8 microfarad capacitor, which would end up being half, would be 4 microfarads in the 0.00004. And if you multiply it all out, it comes out to 129 millijoules. So what I'm getting at is, if you look in our literature, we tell you that in the E3 mode, you're going to be looking at 125 millijoules. As usual with Ultronic, we always lean on the conservative side. So that's where that 125. And if you bump down to E2 with the CPU 95, you're dropping down to 100 millijoules. And then in E1, you're down to 75 millijoules. So I just wanted to put that in there so that you understand that just because one voltage is higher than the other doesn't mean the ignition system has any more energy. You have to know the capacitor size to calculate any of that. Some of the other CD ignition fundamentals. The primary energy is stored either in a single capacitor or a dual capacitor arrangement within the ignition module. And that becomes pretty important, especially when you're setting up tachometers, which we'll talk about in a slide or two down the road here. And then a fully charged capacitor is electrically connected to the appropriate output. So all the distribution's done inside the CPU box or the DISN box or whatever ignition box you have. And then the third bullet point, the ignition coil is basically just a step-up transformer that steps up the voltage anywhere from, say, 100 to 350 volts, all the way up to 33,000 to 50,000 volts. And that depends a lot on the coil design. So 33 on the low end coming out of, say, an integral coil, and you can get as high as 50,000 volts depending on which coil you're talking about. And that voltage kV demand needed to jump the gap or ionize the gap of the spark plugs depends on many things. And then, of course, the higher the voltage, the higher kV, the higher the counts you see in the CPU 95 or CPU 2000, which most of us are familiar with. As the kV goes up, the counts goes up. As the kV goes down, the counts go down. This was taken right out of a Champion spark plug magazine book, so we plagiarized this slide here. But you can see on the left-hand side, the high voltage or the higher kV may be required if you have high compression versus low compression on the right side. So a lower compression engine will take a lot less kV than a high compression engine. And then the next bullet point down is the top dead center versus advanced or retard, where the piston is actually lower than top dead center. The voltage will be down, and the higher you, or the top dead center where the piston's at the top, pressure will be the highest, and you'll have the highest voltage required. Same with speed and load. The higher the speed or the higher the load on the engine, the higher the kV demand from the ignition systems needed. And then electrode temperature. When you go to start a cold engine, you're going to have the highest demand needed. Once the plugs warm up, the engine warms up, you'll see the demand actually drop off some from the ignition system. And then as far as the electrode condition from the spark plug, it'll never be lower than the first day you put that plug in with a well-defined fine edge. Gap is as small as it's ever going to be. Then that's going to be your lowest voltage demand. And as that electrode wears and the ends round off and the gap grows, then of course your demand will go up with it. So that's the next point down is gap space. It's obviously easier to fire a 12,000 gap than it is a 15,000 gap. It takes much more voltage to ionize that extra 3,000 gap. And then lean burn versus rich burn. Lean burns are tough right out of the box. So basically day one, they may take 20,000 volts to ionize the gap of the spark plug on a lean burn engine. There's not much fuel in the cylinder, as opposed to a rich burn that can take 5, 6, 7,000 volts. They can be very low since there's so much fuel mixed in with the air in a rich burn engine. So this is all the things that can make your counts go up and down if you're looking at a CPU 95 or CPU 2000. This is basically an oscilloscope pattern, and we bring this up because with the high voltage probe or 1,000 to 1 probe, we're on a 5 volt scale here, so 5 times 1,000 to 1 probe, each one of these squares ends up being 5,000 volts. So in this particular spark or ionizing the gap of this particular spark plug, you can see that vertically you've got 1 square, 2 square, 3 square, 4. So you're at about 4.5. So this is about a 22,000 kV voltage demand on the left-hand side of the screen there to ionize the gap of that spark plug. You're looking at about 22,000 volts. The rest of the energy is going to be used in the arc duration. So let's say we're in E3 and we've got that 129 millijoules that we just talked about earlier, and say you're putting out 40,000 volts out of that ignition coil, then you're going to be using about 22,000 volts just to ionize the gap. The rest of the energy is going to be used to keep the spark going, or down at the lower end there, it's considered arc duration. So that's how long your spark's going to last. And it's 200 microseconds per division. So we've got 1, 2, say 2.5. So you've got about 500 microseconds of arc duration in that spark there. Now, what would happen if this is considered E3 in the CP95 and we bump down to E2? You've now gone from 129 millijoules down to 100 millijoules energy. That voltage demand on the left-hand side didn't change because your compression pressure didn't change, your spark plug gap didn't change, your air-fuel ratio didn't change. So that 22,000 volts is going to stay the same, but now you've dropped from 129 millijoules to 100 millijoules, so that spark duration is going to have to drop down. So if this is a depiction of, say, 500 microseconds, you may be down into 375 microseconds as an example when you bump down from E3 to E2. I left this in here, and basically this is an old standard mechanical ignition system, say a depiction of, say, an Ultronic 3 for an example. And in the left-hand side, you'll see the alternator. So we all know there's a stator rotor that's being turned by the engine, and that's producing AC. It's coming into that FWR, or full wave rectifier, and that's being turned from AC to DC to then go and charge the capacitors on the circuit board that will then be discharged out to the primary side of the coil. So if on the right-hand side of that dark black line, you'll see a P. That basically is a pickup coil that was many thousands of fine wire, about the thickness of a human hair, say. And whenever the mechanical arm from the Ultronic 3 that has a magnet on it came over top of that pickup coil, it would induce a voltage into that gate of that SCR1. And that would actually turn that silicon-controlled rectifier on and allow the capacitor to discharge out to the primary side of the coil. So if we're talking about Ultronic 3 these days, you're looking about 200 volts getting to that primary side of that coil, and then that's turned around and turned into, say, 40 to 45,000 volts, depending on coil. And that's going to then ionize the spark, jump the gap, the spark plug, and fire your engine. So that's an old mechanical type system. And if you were looking at that G lead or the shutdown lead on an oscilloscope, this is what you would actually see. So this is the primary pattern, or every firing of that capacitor discharged the primary side of the coil. Again, you're down below here. We're just looking at it with a standard probe, so it's 50 volts per division. So you can see 1, 2, 3, slightly more than 3 divisions vertically, and that's telling me that I've got about 160 volts, which is showing up on top there. That ignition system's putting out 160. So that might be an old Ultronic 3, maybe an Ultronic 5 system. And then you can see when you trigger off the number 1 coil, then you can see that the far left-hand side is cylinder number 1, cylinder 2, and across to the right-hand side of the screen. The reason I bring this up is this next primary pattern, and you can see that we've got a problem here, that one of the cylinders isn't firing for some reason. You might have a switch that's gone bad. You might have a broken wire in the harness. Something's acting up, and you'll see it with an oscilloscope, and this is what it would end up looking like. This came up as I go on here. I'll bring up some of the problems we've seen in the past from when I was inside the factory, and then some of them are from when I was outside, out in the field. But this particular issue came up when I was in Kentucky a few weeks ago. I got a call that a customer had a CDISN, which was a CAT DISN ignition system on a 3400 engine, and the problem was they thought the new tach was bad. Then it was suggested that they may have a single versus dual cap issue, and maybe it was set up wrong. So when I asked what the RPM was on this 8-cylinder CAT engine, they tell me it was 1,000 RPMs. And but the tach was only reading 875. So I immediately knew that it couldn't be a single versus dual capacitor issue, because then that tach would be either double or half of 1,000 RPM if it was a single versus dual cap issue. So since the tach was really just a counter that counts the primary pulses, and there should be 4 per revolution on an 8-cylinder 4-cycle engine, I took the 1,000 RPMs divided by the 8 cylinders, and each primary should count for about 125 RPMs. So 1,000 minus 125 would be the 875 that it was showing. So I recommended checking the primary signals with a timing light, and I was told later that day that they had a broken primary to the coil. So what I'm getting at here is this timing light is probably one of the best 2 or 3 tools you can have in your truck or in your toolbox. So basically, I would always recommend having a timing light with you when you go out to troubleshoot these engines. The CD ignition system technology have evolved through the primary phases over the last 40 years. So it started out with solid-state, self-powered mechanical systems, that being the Ultronic 1, the Ultronic 2, the 3, and then the 5. And then we've moved on probably in about the 80s to the CPU system, and then also the event-triggered systems, which is the CEC, the CDISN, which is the CAT DISN, the CD1, and the CD200 systems. And then in the 90s, the 95 and the 2000, which are also crankshaft reference systems that replaced the CPU 90 and the CPU 2. So basically the mechanical system, they work great because they were self-powered. They eliminated the breaker point system, which any of us old-timers that had cars that had breaker points knew that they were a maintenance nightmare. You had to adjust them, and they wore out occasionally. So the solid-state Ultronic system was a big step up and very popular. We've probably sold, I mean, I don't know the exact number. Dave may know better, but I wouldn't guess that we've sold 100,000 of these Ultronic 3s over the years. So we're getting very close to that numbers, and there's still
good close number, Paul.
About 100,000 of them, yeah, and that's not including the 5s or the 1s or anything. We're just talking Ultronic 3s. So, and then the modular back cover design was also a really good idea, because if you had any problems, you basically replace the back cover and be up and running fairly quickly. Now, one of the problems with this system is the accuracy of the timing. Now, inside the mechanical system, you've got a set of gears, and you don't really lose that much timing inside of the system itself, probably less than a half a degree. The problem comes with the engine and the wear parts in these engines, as some of them are 30, 40 years old. And the gears and the chains that stretch and the wearing, you end up losing the timing accuracy on the engine sometimes between 1 and 3 degrees. So cylinder 1 might fire at 24, but cylinder 2 might fire at 22. Cylinder 3 might fire at 21. So basically, depending on the gears and the wear and the chain, you could have timing accuracy off 1, 2, 3 degrees, and that's not good when you're trying to get the most horsepower, the best fuel economy, and the least vibration out of an engine when you have this kind of timing inaccuracy on an engine. So that basically brought up the event-triggered digital system, the 1 pickup system. So that's true that, like I said, the DISN, the CD1, CD200, where you have one Hall effect, and when it came to the CD1 or the CD200, it could be a magnetic pickup, but it's looking for an event. So that may be a magnet or maybe a magnet disc shown on that drawing there. And every time it saw a magnet or a hole, in the case of the CD1 or CD200, it would fire. Now this timing accuracy was pretty good, but it was as accurate as the person drilling the holes, or in the case of a disc, those were done on CNC machines, so they were very accurate. But if you had a customer that had a CD1 or CD200 where they drilled the flywheel themselves or they drilled the harmonic balancer, the timing accuracy was basically as accurate as they drilled the holes. So you may have somewhere between a half and 1 degree timing accuracy coming out of a one pickup system like this. But some of the pros are that it eliminated all the moving parts. So you had none of the bearings and gears and so forth that were wearing out. So these systems were pretty popular, put on at the OEMs and by all the distributors. They were also externally powered. So that was a huge improvement as far as starting goes. You had 24 volts or 12 volts, depending on how the system was powered. And as soon as that unit started to turn, you got the full energy out of that system, as opposed to the mechanical system where if the oil was cold and the cranking was low, you've got pretty low energy, and sometimes the engines would not start if you had a 0.5-to-1 drive, which we'll talk about a little bit later here. But in any case, with these systems, with 12 or 24 volts, you had full power as soon as you started cranking the engine, which made it very popular. And then, of course, the flexibility in the application and the mounting location. It really didn't matter where you mounted this unit. You didn't have to mount it on the drive or anything like you do a mechanical system, so that was a big plus too. And then this unit had LEDs, so you had some very basic diagnostic capability. It showed you the pickups were firing. It showed you that you had DC power and so forth. So this was a big step up from the mechanical system. As far as the best, as far as I'm concerned, is the crankshaft reference digital systems. Now this could be either 2 or 3 pickup systems. Some of the pros are, again, you had no moving parts. It was DC powered. You had improved ignition timing. So this system, if you had 360 holes drilled into flywheel, that would give you a leading and trailing edge pulse from the magnetic pickup looking at the holes in the flywheel. That gives you 720 pulses. We then multiplex that via the inside the CPU and double that. So you ended up with 1,440 pulses in 360-degree revolutions. So your accuracy was basically 0.25 degrees. Hard to see on a timing light, but very accurate. So with the older CPU 2s and 90s, you had a 0.5 degree, and when the 95 and the 2000 came out, that was multiplexed, and it got down to a 1/4 degree accuracy. So very, very accurate. Another big plus was this unit had, the 95 and the 2000s have advanced diagnostics, because they do have a microprocessor or a brain inside of them. They can tell you many, many things. And also, one of the things that comes up is if you're missing plus or minus 5 holes or 5 gear teeth, it would immediately come up, shut your engine down, and tell you, hey, we're missing 5 teeth on the flywheel, and we shut your engine down, and you need to weld them up or fix it. And there's a reason why I brought that one up here. But you also had spark characteristic control. You had E1, E2, E3, which basically allowed you to change the energy out to the coils. Like I said, E1 in 95 was 75, E2 was 100 millijoules, and then E3 we calculated earlier being 125 or 100 millijoules. With the advancement and the microprocessors, basically the Modbus communication became a big thing in the 95 and the 2000s. Now, the reason the 2 or the 3 pickup systems for anybody that's new, and I believe we have some people from overseas that had asked me questions about this earlier. So the 2 pickup system, you always had to have 2 magnetic pickups, no matter what CPU system you used. The reason is one of the magnetic pickups shown down there in the letter D in the bottom of the right on the drawing is one of them was counting either the holes you drilled in the flywheel or the ring gear teeth, and that allowed us to know where that crankshaft is at all times. And the second pickup is basically the same type of magnetic pickup, only it's looking for a reset pin, which allows us to know that we're on the number 1 cylinder and that it's made a complete revolution and to start back on number 1, then 2, then 3. So it gave us a pulse every revolution. So those 2 pickups are a must no matter what engine they're on. But in the case of a 4-cycle engine, we needed that 3rd pickup, which is in the upper right-hand corner, or that Hall effect pickup, and that needs to be mounted at camshaft speed or half engine speed. And what that does is it masks out every other reset pin. So if this is on a Caterpillar 16-cylinder engine, and it's a 4-cycle engine, we'll see the reset pin on the first revolution. We'll fire cylinders 1 through 8. Because of that magnet will be 180 degrees out because it's mounted on the camshaft that's going half engine speed, it'll mask out the second reset pulse to the CPU. And since we don't see a reset pulse because those two aren't in sync, it allows the ignition to fire cylinders 9 through 16. And then on the next revolution, they're back in sync again, and we get back cylinders 1 through 8 again. So for those people that don't know, that's why we have to have that third pickup on a 4-cycle engine, and it ends up being a Hall effect pickup, which we'll talk about in a minute here and show you how to troubleshoot them and so forth. But that's why some systems need 2 pickups and some need 3. So as far as the magnetic pickup goes, up in the upper left-hand corner I put in red, don't crank on the knurled connector, because this has happened many times. That connector there is pressed on there. And if when you go down and crank on that jam nut and you have a pair of channel locks on that knurled nut, people will pull that off of there. Like I said, it's just pressed on there, or they'll twist the keyway or the pins inside that connector, and they'll damage that pickup. So what I like to do is get the gap right, turn down the jam nut, and then put the channel locks on the threads right below the connector there. Those threads are never really used anyways. That's where I hold it when I tighten down that jam nut, and I don't put the channel locks on the knurled nut there, because you can twist that off or damage the keyway or break the pins. So just be careful. That happens a lot. So, so down in the lower end of the drawing there, it shows you this is basically a rare earth magnet that's very, very long but very thin. You can see the diameter is only 106 thousandths of an inch. Then you've got a few thousand turns of fine wire wrapped around that, and it pulls out to the 2 pins, A and B. So this ends up being a little generator. So if you put this on your engine and it's looking at gear teeth and there's nothing hooked up to it, you could put a voltmeter on A and B and you'll get the voltage coming out of it, because you basically created a little generator here. So because this is intrinsically safe, we don't ever want it to create any sparks. You've got 2 sets of Zener diodes in there. So there's 2 redundant sets of diodes that are going to limit this device, that it'll never put out more than 16.4 volts peak to peak. So you can run it and touch the A and B wires together, short them out, and you'll never create a spark, which basically makes it intrinsically safe. And having said that, this device usually is only putting out, say, 3 to 6 volts. And very seldom do you see much higher voltage than that, even though we will clip it at 16.4. You're usually never getting to that point. I did put in the reset pin fabrication details, because one of the things that you should pay attention to is the pole piece diameter. So depending on what pickup you're using, in this case we're talking about our pickup, it's got 106 thousandths pole piece. It's a good idea to take that 1/4 pole that's shown here and then grind it down on a grinder to where the flat top is about the same diameter or the same thickness as the pole piece. So 100 thousandths in this drawing, and the pole piece in the pickup is 106 thousandths. So what you're trying to do is make it about the same thickness as the pole piece. Again, one of the other things we've seen many times is that somebody takes a stainless steel bolt and makes a reset pin out of it, and then of course it won't trigger the magnetic pickup. So that's another thing to be aware of, is that you make sure you get a ferrous metal bolt that attracts to a magnet. The magnetic pickup output, that depends on a few things here. The amplitude of the output voltage depends on the surface speed of the gear, the gap between the pole piece and the gear, and the gear tooth size and spacing. So that's the pitch of the gear, the size and the spacing, and then the load impedance. The pickup output voltage is directly proportional to the surface speed of the gear. So the surface speed is most often expressed in terms in inches per second. So one rule of thumb is if you can have two gears that you can put this magnetic pickup on, you've got a 4-inch or an 8-inch, you'd always want to pick the bigger one. You want the inches per second to be higher if at all possible. So, and then the magnetic pickup, here's some little bit of troubleshooting. Say it's a 2-wire non-powered device that generates its own voltage as discontinuations of ferrous metal passes by. It's a 5/8 18 thread. So the gap, a lot of times you can't get in there with a feeler gauge to set the 15 thousandths gap. So if you look in the manual, it's 15 thousandths plus or minus 5. So if you take that 18 threads, 5/8 18, the 18 means 18 threads per inch. If you take 1 inch and you divide it by 18, that basically tells you it's 55 thousandths per revolution. So what I usually do is I screw it in flush up against the flywheel or to the top of the gear, mark the 12 o'clock position, and then back it out 1/4 turn, and that'll take your 55 thousandths divided by 1/4 or 1/4, and you end up at 14 thousandths gap. And I'd say more than half the times you can't get in there with a feeler gauge and set this 15 thousandths. So that 1/4 turn is a good, easy way to set it, and it's worked every time for me. So I'm pretty sure it'll work for you. So that'll give you a 14 thousandths gap. Because the pickup has such low output, if you get either oil or glycol or antifreeze in the connector, it will cause that magnetic pickup or the Hall effect to short out. So you want to make sure that the connectors are on tight and you're not leaking oil or glycol onto them where it could short these devices out. And then the other thing is, don't share the magnetic pickups with other items. They are such low output devices that they can't share their signals with governors and tachometers and so forth without running into problems. So we never recommend sharing magnetic pickups. This is what you may see and why we recommend people pulling them out, especially if you have ring gear starters. If you have air and head starters, it may not be as big a deal, but when you have little shavings or metal dust coming off as that ring gear starts that engine every time, this rare earth pull piece is so strong that it'll actually attract that shavings or dust, and over time it'll attenuate the signal out of the magnetic pickup. So in those cases, I'd say once a year or so, pull that out, wipe it off, run it in flush up against the flywheel, and then back it out 1/4 turn, and then tighten down the jam nut. Like I said, not without turning on the knurled part of the pickup where you can damage it. So this is one that came out that actually was having problems, and you can see why. The pole piece is completely covered up. This is one Mike's going to talk about, but I mentioned earlier that one of the diagnostics is plus or minus 5 gear teeth, and your engine's going to be going down. If you say you need 360 teeth and you're only seeing 350 or 355, that engine will go down. So it's plus or minus 5 teeth. In Mike's case here, I got a feeling his engine run just fine because you can see that it looks like there's 4 broken off teeth on this flywheel. So the engine probably stayed running just fine, but then ran into other issues, which Mike's going to talk about right now.
We had an engine analyzer guy on this, and this was on a CPU XL on a Cooper GM. It started out to be a GM BC, and they redid it to make it an H. They took off the mitter blower, but what they were having on this 10-cylinder, last 4 cylinders, the timing was only at 4 degrees before top dead center when everything else was set up at 8. And of course, the ignition was programmed at 8. So they swapped out and he picked it up with the analyzer, and sometimes if you don't line up the encoder right on the flywheel, you can get a whipping effect on the analyzer. So I said, well, are you sure you're straight? He said, well, we verified it with a timing light. So I said, okay, it's got to be accurate then. So anyways, they went through and swapped out some parts and stuff on it, and of course it never did go away. So we got there, and I said the engine ran fine, but the RPM was off a little bit. You know, with those teeth being gone, it's looking for 366 teeth, I think is what it was. So and it was missing 4 of them. So the RPM was off a little bit on it. So they also noticed that. So anyways, we got in there and we were able to shut the engine down and actually talking to Tom Smith and explained to him what happened. And I mean, Tom nailed it right on the head there that he said, I think they're missing some teeth. And they have 2 starters on this engine. So even though those 4 teeth are gone, the other starter will push that other starter through those broken teeth, so they were able to start the engine. And it had just enough teeth where it didn't trigger the CPU 2000 or the XL or the 2000 on not enough ring gear teeth, so it would have triggered it for a shutdown. So it was an interesting find. What they ended up doing to keep the thing running was they actually went in there and did a 3-degree offset on each of those cylinders to get it so it would fire close to the 8 degrees, so to keep the engine running. But I told them eventually, you're not doing the starters any good because they got to be chewing up when they went through that area. I says, as soon as you knock another tooth off there, you're going to lose the engine because the ignition is going to finally shut it down. So if you do run across that a situation like that, go look at the gear teeth on it, and you'll probably find some missing. So that's it on my end.
Mike, this basically come right out of the application list, and I just wanted to bring this up because when you go to mount the magnet, and you need to mount that magnet at half engine speed, the 1.5 to 1 works out just perfect also. So I ran into this a couple of weeks ago when I was installing the 95 on a Waukesha engine, and it ended up having a 12A33, which if you look down here to the Cat 398s, that's the same model on there. So if you look at that model, you know that the unit has 3-to-1 gears in it for the 12A, and then that first 3 tells you what the gears are inside of it, because the back cover needs to be going half engine speed. So it's a 1.5 drive inside the engine. Then we've got 3-to-1 gears inside the Ultronic 3. So I knew that being that it was a 12A33, it has 3-to-1 gears in it, then the engine drive had to be 1.5 to 1. So that allowed us to use that drive to mount the magnet, which I'll show you here in a minute. But it's nice to go back to these application lists and see what the drives are, see what the systems are, and you can basically help you out when you go to mount the magnet for the CPU 95 or 2000 or whatever you're installing XL. So just a little explanation of the engine drive ratio for anybody that's new. So an example is the engine's 1,000 RPM and it's a 4-cycle engine. If it says 1-to-1, basically the crankshaft's considered 1-to-1. So the drive gear is going 1,000 RPMs also, the same as the engine. If it says half to 1 drive, then that's basically what a camshaft is too. So it's half to 1. Since the engine is going 1,000 to 1, this drive's half to 1. That engine drive is going 500 RPM or the same speed as the camshaft. This is great for mounting the magnet for a CPU system. It's not so great if you're turning a mechanical ignition system that may start in the middle of summer, but with when the engine gets cold and the oil gets thick and you drop from, say, 120 cranking RPMs down to 80, your engine may not start. So this has never been a good drive for a mechanical system, a half to 1. I mean, you really want a 1-to-1 or higher, but there are applications with half to 1s out there. And then when it says 1.5 to 1 engine drive, this means the engine drive is going 1.5 times the crank. The crank we know is going 1,000 RPMs, so this drive is now going 1,500 RPMs. This is a great drive for mounting a Hall effect magnet or a mechanical ignition system. And I'll show you why here in a minute. So the Hall effect pickup, two real easy drives to install the magnet on are either half to 1 or 1.5 to 1. And again, refer to the application list. The good rule of thumb here is if you're using a small magnet, try to keep it in a diameter of 3.5 inches or smaller. And if you're using the large magnet, which is the 5/8 inch diameter or over twice the size, then it's a good idea to try and keep the diameter, say, 7 inches or smaller for the large magnet. That's a good rule of thumb. And the reason why the half to 1 and the 1.5 to 1 work so well, as you can see up here in the top 4 circles, that's the crankshaft. So every revolution, the reset pin is at at top dead center there at the noon position. Okay, if you go down to the camshaft, which is the next 4 circles in the middle there, that's half the one, or representation of a camshaft. And you can see the first circle, they're directly in line. So you'll fire on a 16-cylinder 4-cycle, you'd fire 1 through 8 cylinders. On the next revolution, you can see they're 180 out. So that CPU is not going to see that second reset because they're 180 out. The magnet's not aligned when the reset pin is aligned with the magnetic pickup. So then you'll fire cylinders 9 through 16. On the third circle, you'll see they're back in line again. The engine will go back through cylinders 1 through 8 again, and then the fourth one, 9 through 16. Now, if you go down to the bottom 4, this is why it works so well, because 1.5 turn, 1.5 to 1, basically, if you use the circle and you draw it out, you can see that 1.5 to 1 ends up emulating the half to 1 drive exactly. And the CPU doesn't care if it went 1.5 revolutions as opposed to half. As long as they're in sync when they need to be, that's all the CPU cares about. So this is why it makes life easy if you can mount the magnet on 1.5 to 1 rather than drill the cam cover and drill a gear that's usually hardened that's not easy to drill. So this makes life extremely easy if you have a 1.5 to 1 drive. And in this particular case, on this Waukesha 7042 that I was helping to replace the 95 on a few weeks back, this is what we had. That 12A33 Ultronic 3 that we're pulling off, 3 to 1 gears. The engine drive had 1.5 to 1 gears. So that made life extremely easy because all we did was we took that figure 8 coupling off, we took the Ultronic 3 off, and we drilled right here, if you can see my pointer, an 8mm hole, and we mounted the big magnet right there in that figure 8 coupling, the middle part of it. And basically it was quick and easy and made life easy. So here you see it all done. So we mounted a piece of metal channel, drilled and tapped the 5/8 hole for the pickup, mounted that large magnet, and then put a cover over it for safety. So it made life pretty quick and easy without having to drill cam covers and harden gears and so forth. As far as testing the Hall effect, pretty easy to test these. There's 2 types of Hall effects. There's a sinking and a sourcing. So just be aware that the Hall effects that's used in the CPU systems is the 591014, and that's considered a sourcing pickup. And the other one is considered a sinking pickup is 791050. That's for the DISNs and the CECs and so forth. So you have to be careful because they look the same and they both have blue labels, and the only difference is the part number and how they work. So if you screw them in the wrong system, they will not work. So be careful that there are 2 different type Hall effects that look very similar. But if you had to test the Hall effect out on a bench, if you had a power supply, you can put 8 to 12 volts in it. If you don't, if you just had a transistor battery, 9 volts, and you connect it up here on plus and minus, it's tied to the positive is the B pin, the negative is the C pin, and then A is your switch. So if you took your voltmeter from the negative, which is C, over to A, and you put your magnet in front of that Hall effect, you're going to see your 9 volts from your 9-volt battery over here on your voltmeter. You pull the magnet away, and the voltage is going to drop to 0, and put it back, it'll go back up to 9 volts. So pretty easy to test this device. The thing about these Hall effects is they are looking for a north pole. So if you have one of our magnets, obviously it's going to be north pole facing out. But if you just pull a magnet out of your desk or something like that, and it's got the south pole facing it, it will not trigger. So try it, flip it around and try the north pole. Make sure you have to see a north pole to make the device trigger. So just be aware that if you're troubleshooting it, that's one of the cases. And we've had this happen where somebody pulled the magnet out of an old Ultronic 2, which is a 5/8 diameter in a brown phenolic case, and that actually is south pole facing out. And people try to use that magnet, and it will not trigger a Hall effect. So just be aware of that in case. Some of the common ignition problems: infiltration of water or oil will cause you problems. Extreme vibration will cause you problems. exposure to excessive heat will cause you problems. And I put in parentheses here the CAT 3400. They have actually mounted the Ultronic 3 down in the V on the CAT 3400s, and it got so hot in there that it actually caused failure of the systems. So in the long run, they ended up getting rid of the mechanical drive inside it, and basically they went to a CDISN or a DISN type system on those CAT 34 series engines because of that excessive heat down in that V. So just be aware that temperature could get you if you don't pay attention to where you're installing items. An inadequate power supply can cause you problems. Improper installation, poor wiring practices, of course, will get you. And probably the biggest thing, and you can talk to Tom or me that did a lot of inside work. Or technically, grounding is probably your biggest issue. If you don't do that right, you're going to be chasing problems for the next 20 years. So the grounding is the main thing when you install the systems. RFI, we recommend that digital ignition systems should be operated with resistor spark plugs and or secondary leads. So we'd recommend, say, 5,000 to 10,000 ohms in the secondary path. And it's always best to have the resistance closest to the spark. The closer to the spark, the better the attenuation of the RFI. And then, of course, maintain your secondary wires and your boots. There was a customer not so many years ago that had a fire, and basically they wanted to know what they could do or why it happened. They went in there at midnight, turned the lights off, and it looked like the 4th of July. Well, these secondary leads ended up being about 12 years old. So if you just multiply out the 24 hours in a day, 7 days a week, times 8,000 hours a year, times 60 miles an hour, those engines basically had about 5.7 million miles on them if you equated it to a car. And they still were running them 12 years later. Then they wonder why they're creating sparks and in the end created a fire. I mean, you can't run these, you'd never try to run your car leads for even 200,000 miles, let alone 5 million miles. So basically, you have to keep up on the leads and replace them, and they don't last forever is what I'm getting at. Proper spark plug installation. There is a torque spec, and maintenance is critical. So on that 7042 that I was talking about, the guy's installing new plugs. He has 5,500 hours on them, so about 3/4 of a year, say. And he goes and he starts cranking on it, and I asked him, I said, well, what kind of torque are you putting on there? He was using a torque wrench. He says, well, I like to put them in at 50 pounds. And these are 18 millimeter plugs. And I told him, well, the torque spec's 35 pounds. And he says, well, I just like to have them nice and tight. Well, we all know that that's a bad idea. I mean, when you stretch the threads, you damage the seal inside the spark plugs because you over torqued them. You're going to have nothing but problems. So I explained it. My guess is he's still cranking them down to 50, but all you can do is lead the horse to water, right? So in any case, use the proper torque when you're putting plugs in. Basically, 14 millimeters, 24, 18 millimeters, 35, and 50 for a big 7/8 plug is a good rule of thumb. Maintain separation between all the primary and secondary wires. If you don't, you can run into problems. We ran into a problem back at the factory years ago where they had an engine going down on so many teeth. I think it was 128 teeth or so. And after talking to the distributor, and basically we found out that 128 teeth ended up being like 8 left. They go out to 8 left, and the secondary wire is leaning up against the CPU box. And it's inducing the RFI into the box and causing the engine to go down on startup. So once they pulled that secondary wire off the side of the box leaning up against it, then the problem went away. So it's critical to keep the distance between, especially the secondaries that may be putting out 40, 50,000 volts. And then proper grounding is very, very critical. I mean, Frank Revisa pounded this into our head, and he couldn't have been more right. I got called out a few years ago to a site, and I'm just putting in a few examples just for keep it from being too boring. But I got called out to a remote site on a CP2000 where one of the first things I checked was the negative side of the power to the earth ground. And we should see 1.5 ohms to ground, but I'm reading 13 ohms on this particular system. We then proceed to clean all the grounds, remove all the paint, and once we are all done, the resistance is then rechecked, and we're down to about 1 ohm, and all the problems go away. So what I'm getting at here is 13 ohms to ground is not a good ground, and it will cause you problems. So, remove the paint and so forth. Proper wiring practices, use proper sized conductors. So there are wire charts in the CPU system, so pay attention to them and use them, or you will get low voltage A, low voltage B, and you'll have problems. So you use the wire charts that are in the installation instructions. Size the conduit generously to avoid abrasion and stripping. So one customer that I know of has a rule of thumb that the conduits can't be no more than 40% full. So I was out on a Save Air site many years ago, and the unit was blowing fuses left and right. We opened up the conduit, and it's stuffed so full you couldn't put a toothpick in there. So that's what an example is. Use the right size conduit and don't jam them full, or you will run into problems. And again, like I said, some of the customers have their own rules for this. Keep all your wiring runs as short as possible. Run all pickup, thermocouple, and communications cables separately from other wiring. And that's mostly because these particular signals are usually below a volt or a couple of volts. So you want to keep them away from the high voltage because they are such low voltage devices. Thermocouples are 100 millivolts or 150 millivolts, so you got to keep them away from all that high voltage stuff. Main separation between ignition and secondary cables we just talked about. And then, of course, common sense, don't stretch the cables. Route wires clear of high temperature, staying away from cylinder heads or exhaust manifolds or especially turbos, or they'll burn the insulation right off of them. Never store excess wire loops inside the ignition enclosures. I think we've all seen this happen where they got an extra 20 feet and they just wrap it up and stick it in the junction box. This is always a mistake. Keep spark plug wires as short as possible, and that's especially true with the shielded secondaries. I mean, an example of this, we had a customer call years ago, and they mounted the coils like 39 inches away from the spark plugs, and they wanted secondaries made special for them that were longer, like I said, 40 inches or so. I asked the old owner, Bruce, who a lot of us know, if we can make these special ones for him, and he said, absolutely not. Tell him to move the coils, which, of course, is the right answer. The longer the shielded secondary leads, the more energy you lose inside of those metal shielded secondary leads. So keep them as short as possible. Again, another rule of thumb is never paint secondary leads. Use proper termination practices. This is one of Frank's old drawings here, and I had to use it. Now, out in the field, you may not be able to apply solder, but it's a good idea to when you strip it to actually see the copper conductor coming out the end before you recrimp it. And I see more problems, not so much with these ring terminals, but in the Phoenix connectors that we use inside the CPUs and so forth. If you can't see a little bit of the copper wire sticking out of those Phoenix connectors when you screw them down, then you can run into problems. We've seen that where they actually screwed them down on the installation and they've got no connection inside of there. So it's important on the ring terminals, but it's also important on these green Phoenix connectors to be able to see the copper conduit when you screw down the screw. Grounding grounding is the most important thing there that'll save your butt as far as problems in the future. So follow installation instructions carefully, making all recommended ground connections. Connect the wire shields at one end and one end only. If you connect the shield wire at both ends, you've created a big antenna, and now you've created problems for yourself. It only gets connected. That's why the magnetic pickups cables are the shields connected inside the CPU box, but not out there at the pickup itself, one side only. And then the power supply negative must be grounded to the engine block. And then, of course, the engine block should be grounded to earth ground, so that basically creates your earth ground. And then connect the wire shields together if extending a wire that has a shield. Now, this example here really kicked this distributor's butt for a couple of days and really had the customer upset. what happened was the customer was down for extra few days when the extra 50 feet of magnetic pickup wire was added. But what happened was the installer had connected the red and black wires together, but never tied the two shields together when extending the extra 50 feet. And then he pulled it through the conduit. So then when the 2000 was started, the engine would go down on 168 teeth every time they go to start it, and they couldn't figure out why. Of course, you take a meter and you measure the magnetic pickup cables, and red to black was great. There was no it didn't conduct from red to shield or black to shield, but nobody knew inside of that conduit the shields weren't tied together. And that RFI got this particular site and had them down for a couple of days to solve that issue. So that if you'd have just tied the shields together, the problem would never came up. So be careful when you're extending pickup wires. If you're gonna do that, make sure you tie the shields together. Proper grounding practices. Ensure that all grounds are made to bare metal surfaces, free of the paint, free of the grease, rust, and other foreign materials, or you won't get a good ground. And like I said, 13 ohms, the ground is not ground. The ignition case must be well grounded to the engine block. The CPU's stainless steel ground strap across the shock. This can get you if this is loose or if you don't put it in the right corner. So a lot of times people will pull the shock mounts out, put it up on the metal plate, drill the 4 holes, and then the stainless steel strap that's grounding that CPU box ends up in the wrong corner, and then the box has no ground. So in this, you can see here, this is a picture of a CPU95, and if it's not in that lower right-hand corner like you see in the picture, then you're not getting a good ground because we didn't remove the paint from the other 3 corners. So make sure it's in the right corner or remove the paint from the other ones yourself. But here's another thing. On the 95s, it's in the lower right. And on the CPU 2000s, it's in the lower left. I wish we would have put it all in one place, but that didn't happen. So be careful where you put it because it does change depending on which system you have it on. If that thing isn't grounded well, it can cause you problems. We had a customer within the last 2 years that had issues that their tack was shutting down on them. And when we got out to the site, all it was that ground strap was loose. We tightened down that ground strap and his tack quit acting up and quit going down on overspeed. So that's an important part right there. It needs to be in the lower left hand or lower right hand corner on the 95, and it needs to be tight. So just be aware that that can cause you problems. This particular drawing I put in here, you've all probably seen this before, but what we're getting at is grounding, grounding, grounding. You can see all the coils are daisy chained together. You've got to ground at the front and the back of both banks, both right and left banks. You can see that they're grounded. They come into the CPU junction box, and you can see we've got them grounded in 3 different places. So the reason that is we know that the metal plate in there is all at the same ground potential, but we're trying to get rid of as much RFI and as much noise as we possibly can. So we want those in 3 different corners of that junction box and not stacked together, which we see all too often. And I know the Aegis guys make them fix it if they see it in the field because I've been with them. And this is what it looks like inside the junction box. And some of the customers install it and they put them all on the same point. This is a bad idea when it comes to grounding inside of the junction box. Just put them on 3 different corners. And this picture basically is showing you that we ground the heck out of everything to try and keep the problems from happening. So you've got the stainless steel strap in the lower right hand corner on this 95. You've got the J lead coming out of the 19 pin connector on the right hand side of the primary connector. That's another ground for that box. Every coil is grounded, and then you got your spark plug grounded, and then the engine's grounded. So there's tons of grounds, and if you ground everything correctly, you will have very few problems. Some other common mistakes: do not share ignition mag pickup signals for other related equipment, especially governors and analyzers and so forth. There's just not enough signal there to be sharing it. They need their own magnetic pickups. And then this one is very important because it'll save you a lot of time. Always believe your timing light over the very expensive engine analyzer when it comes to ignition timing. I don't know how many times this has happened. Tom can tell you, I can tell you. Within the last year and a half, we got a call where they had a big engine and they were saying the CPU that had been installed for 12 years and running the engine great was now their timing was all over the place. They were 2-3 degrees off on this cylinder, that cylinder. And Donnie had originally called me. I told him it's going to be the engine analyzer that's the problem. He then turned around and called Tom. Tom told him it's going to be the engine analyzer that's the problem. They literally spent 2 days out there with 2 or 3 engineers trying to figure out what it was till they went to the warehouse, pulled off an old dusty beta trap, powered it up, and it proved the timing light was right all along. It was the engine analyzer. So the wind rock they were using had some type of issue or an encoder issue or whatever, but we told them that from day one. So always believe your $150 timing light over the $40,000 piece of equipment. It's a light on a wire, and they don't lie. So it'll save you trips and time and a lot of headaches. Learn to trust and respond to your system diagnostics. If they pop up, they're true. I mean, I'll show an example here in a minute, but do not double fire ignition systems on turbocharged or lean burn applications. Those are the two where you don't want an exhaust stroke fired ignition system, either lean burn or turbocharged. And then the last one will save you a lot of headaches, especially if you're on the phone trying to help people. Ask for pictures. This one here came up just a few weeks ago. Customer says they got low voltage spark problems, and we originally thought maybe they had low voltage A or B problems. Basically, once a picture was sent to the distributor, it was immediately aware that this is just an alarm that was needed reset. And that's all it was, a quick 5 minutes explanation, and they were able to fix this problem themselves. But this is where the picture can save you a lot of headaches and trouble and time. So this example here is just in the last few weeks where a picture wasn't sent, and where Dominion had called with a panel that was going down intermittently on emergency shutdowns or ESD shutdowns. No picture was supplied. And both Aegis and I thought this is a pretty big deal. Let's go help them figure out what this ESD problem is before it gets out of hand. It's this pretty scary thing. But once we get there, we found out it had nothing to do with ESD, which was on 0.57, but was actually going down on 0.60, which was just the manual stop key in this very old panel that looked like it had a damaged manual stop key on this device. So that picture in this particular case would have saved us a trip, is what I'm getting at. So pictures are worth 1,000 words. And then the solid state mechanical systems, you can see Ultronic 1s, the second one's the Ultronic 2, the Ultronic 3, and Ultronic 5. Are they still being used? I would say, with the exception of the Ultronic 2, there are thousands of these systems out there still running. We were at a site 2 weeks ago selling panels, and they had 4 engines running Ultronic 1s. They're all over the place, so don't think that they're getting to be obsolete. The only one that may be hard to find these days are the Ultronic 2s. And then lastly, just quickly going over the ignition accessories. This is the universal junction box, and I work with Aegis, and they've used quite a few of these. One thing to be aware of when you sell them to the customers is they may wire them wrong. You can see they're using the lower part of the Phoenix connector on both of these, so this engine will start right up. But in some cases, what they've done is they use the top row, and then on the other side they use the bottom row, and you can see from the metal connections inside of this that there are no connections. Unless you have the black shorting plug pushing down through the top, those two metal rods are not connected inside at all. So I've seen this with this particular system, but I've also seen it in the field where they added banana plugs on their junction boxes, and then they said the diagnostic module quit working, and they buy another diagnostic module. When I get to the site, all it was is they were using these type of terminals, and they happen to be Weidmuller blocks. And they did the exact same thing. They wired one wire to the bottom and then one wire to the top, and internally there's no connection inside. So pulling out an ohmmeter in 5 minutes, it was apparent that there was never any problem at all. They had just wired them to the wrong connections. So if you can't pull the plastic piece off the side and look inside, you have to get an ohmmeter and actually ohm them. But this happens more than we think in the field. And So I'm just putting this up there to be aware that if the shorting plug isn't in there, then the top and bottom rail aren't tied together. And then ultronic coils. The primary function of the coil is to step up the voltage delivered to the ignition system to meet the voltage demand at the spark plug. A number of factors influence this, and we've gone over this from the champion slide we talked about earlier, but many things change the actual kV demand needed to ionize the gap of the spark plug. What determines the make and model of the coil to be used with the ultronic ignition system? Well, the grounding polarity. So if you got an ultronic 1, 3, 90, 95, CD1, 200, all those systems use negative ground ignition systems. So you'll be using either a blue or a red type coil, whether it's shielded or non-shielded. When it comes to the positive ground, you've got the CPU2, the Ultronic 2, the 2000, the DIS. Those are all positive ground systems, so they'll take the black coil or the shielded black coil. So you have to be careful of which coil you install with the systems. They have to be correct. And then hazardous area requirements, class 1, div 2. The system has to be completely shielded. So you'll be using a shielded coil, a flanged coil, which is either the red or the blue flanged coil, and then the integral ignition coils with div 2 requirements. Unshielded coils are suited for all other applications. So some of the construction and some of the benefits of the Ultronic is constructed of 100% and 100% high voltage tested. So we test all these coils before they leave. The windings are encapsulated under high vacuum and heat. The plus side of that is you get rid of all the voids in the epoxy by pulling a vacuum under high heat. You don't want any voids in there when the primary and secondary cause arcing and so forth. And then the higher voltage handling capability. You got longer spark duration in the case of the red versus the blue coil. And then we're testing for durability with open secondary. So we'll run some of these coils for up to a day and then make sure they still work. So a lot of testing goes on. Now, I saw out in the field some green coils years ago when I was out troubleshooting, and I asked where they came from, and I'm not going to mention the OEM, but they got them overseas and they got them dirt cheap. Then I find out a few years later that they quit using them because they don't pull a high vacuum and high heat and do the things that we do, and although they were cheap, they couldn't hold up in the field, so they quit using them. So they happen to be green at the time, but they're no longer used by that particular OEM. And then a few thoughts on ignition coils. Educate yourselves and your customers. Ignition coils are not commodities. Coils are matched, part of a high-performance system. So if you got blue coils, they have to all be blue. You can't mix red and blue and so forth. They all need to be of the same type. Then you get the highest available voltage. You want current in the arc with quality combustion, spark duration. That allows you quality combustion and the spark rise time. And the coils are long-term investments. These devices have to run 24 hours a day, 7 days a week. So it's not the place to skimp on cheap coils. And I don't really see a lot of cheap coils out there in the field. I mean, like I said, those green ones, but they didn't last long out there. Most people know to buy good stuff. And then epoxy coil is used in non-hazardous areas for all applications and typical bolted to a bracket. So there's three versions. The 061 is the blue negative ground coil, probably the most common. The long duration red or the 010 coil is used mostly on lean burns or possibly turbocharged applications. You'll see those. And then the black one is used for all positive ground, CPU2s, Ultronic 2s, and so forth. And then, of course, those same coils need to be put into a metal can for a shielded system. And for a shielded system, and you're using this type of coil, you have to use a shielded secondary and the shielded spark plug to be div 2 rated. If you use this shielded coil and then you have open secondaries or non-shielded secondaries, then the system's not div 2 approved. And that's fairly common here in the States. And then flange mount coils, most of us are familiar with it. CAT uses them, Waukesha uses them. So the CAT systems use the red 08 or 012 coil, and the blue is used by Waukesha, the 018. This is a div 2 approved shielded coil, and it was put on the head, and the Waukesha or Caterpillar sent it out to get CSA approved. So these do meet, when they're mounted with the 3 bolts, they do meet the Div 2 rating. And then lastly, integral coils. I think we got one slide left. When used with suitable shielded spark plugs, integral coils meet Div 2 hazardous area. They eliminate the need for any secondary lead. You should be avoided in high heat areas, particularly on lean burn applications, and more limited spark voltage output. So the thing about these on lean burn applications, where a lean burn engine may pull 20,000 volts to jump the gap of spark plug day one, these coils have less output than the standard coils. So this is why we wouldn't recommend using integral coils on a lean burn engine. They only put out about 33,000 volts, as opposed to a standard coil putting out between 40 and say 45,000 volts. And then there are four different lengths available in this particular model, the integral coils. But again, these coils are used offshore and in Canada, but you don't see a lot of them here in the States. But like I said, they are limited on their output. And then I brought up the safety leads picture mostly to bring up the thing at the bottom, because we've had these ordered in hundreds of them and then ordered wrong. So what I want to get at in these safety leads, if you look at the upper end of the safety lead on the left-hand side, you can see one of them's got a 1-inch weld depth on the spark plug, and the other one's got a 2-inch weld depth. So there are spark plugs that you have to make sure that you're ordering the right safety lead. The coil end's going to be the same no matter what, but the plug end could either be 1-inch weld depth or 2-inch weld depth. And we've had these ordered wrong before, and it's a bummer when you send 100 of them or 200 of them overseas and they're wrong. So make sure you're getting the right weld depth for the particular spark plug that you're using. And these do meet Div 2 Class D ratings. The good thing about these is they're non-metallic leads, add no additional load to the ignition system. So you should get a little longer spark plug life because there is no capacitive load from this particular carbon Teflon outer shell casing. And the other good thing is that most timing lights will work across these, where they won't work across the metal shielded secondary leads. So these are nice leads. And then basically that's about all I've got, and we're about 10-15 minutes over. So unless anybody's got any major questions, we'll call it a day.
Paul, well done. Thank you so much. Very, very important. I really like the examples, the field troubleshooting examples. I think that you really hit a home run with that. Folks, any questions for Paul? Got an opportunity here. Obviously, Paul's got an enormous amount of experience here. We've got some other folks of our Ultronic team on this call as well. Is there anything specific that you'd like to ask relative to the subjects today?
Testing a mag pickup in an integral coil.
Sorry, we couldn't quite hear you, sir.
Testing a mag pickup and an integral coil.
Well, the testing of the mag pickup, I mean, out in the field, usually we do a quick resistance check. And I'm glad you brought that up, because we do have a couple different models of that or changes inside of that pickup. So we're going to say that if you've got anywhere between 800 and 1500 ohms across that pickup coil, that you're going to be calling it a good pickup. And the last thing is, so if you're measured from A to B, you should be seeing that 800 to 1500 ohms. The other thing, though, to always do, because this just came up in the last year, but very, very, very rare, is you measure A to the casing of the pickup, and then measure B pin to the case of the pickup. And of course, you should have nothing from A to the case and B to the case. You should just have continuity from A to B, and it should be between 800 and 1500 ohms. And that's, and of course you don't want any glycol or oil in the end of the connectors, but that's when I'd call it a good pickup. And then look at the end of the magnet, make sure that it hasn't been hit up against the flywheel or a reset pin and been damaged. That's the other thing that you'd want to make sure. And it's clean of any metal shavings that we showed you in that picture earlier. That'd be another something else to look at when it comes to the magnetic pickup. But they're usually a pretty good device that you don't have a lot of problems with unless they've been stepped on as far as climbing up on the engine or damaged by being hit with the reset pin or the gear teeth from the ring gear or so forth. But you can actually pull the 5-pin Phoenix connector right at the CPU box if you have a CPU and measure it all from that. So you're measuring all the way through the harness. So you're looking A to B for that 500 to 800 ohms right there at the Phoenix connector on both reset and gear teeth. And then you measure black to shield, red to shield on both pickups, and you can do both pickups right there at the 5-pin Phoenix connector inside the CPU box. It makes life a little easier. But as far as the integral coil testing, basically, other than sending it back to the factory, about all you can really do is measure the resistance of the primary and the resistance of the secondary. And the resistance of the primary, I can tell you, is really hard to do unless you have an expensive meter, because they're sometimes 0.1 to 0.3 ohms. And I mean, if you just hold your meter leads together, you'll get more than that. So that's tough to check the primary resistance correctly with just a standard, non-expensive meter that's made for that.